Welcome, everyone, and thank you for joining us today to talk about RECs. My name is Carolyn Hironis, and I'm the REC Survey Manager. And today I'm joined by my colleagues, Liz Holland and Greg Lawson, to share some data highlights and information on our end-use estimation methodology from the 2020 RECs. So before we get started, I have a disclaimer for you. So this WebEx call is being recorded and may be posted on DOE's website or used internally. All attendees are muted and will not be able to share video during this webinar. However, if you have concerns, please drop off the webinar at this time. So during the time that we have together today, we're going to give you a brief intro to the 2020 RECs, share some data highlights, talk about our new ArcGIS data visualization tool, and discuss our process for creating end-use estimates. And then we will wrap up with our plans for the next RECs. And there will be some time for Q&A at the end of the webinar. You can submit your questions in the chat box, and my colleague, Bill McNary, will be monitoring the chat. Okay, so I'm going to get started with a brief overview of the entire RECs program and process. So there are three phases to RECs: the household survey, the energy supplier survey, and the end-use estimation process. So let's start with the household survey. The RECs household survey measures the characteristics that contribute to energy consumption in the home. And the unit of analysis is primary occupied housing units. So this includes single-family detached and attached houses, units in apartment buildings, and mobile homes. The RECs does not include seasonal or vacation homes, vacant homes, or group quarters, like college dorms or military barracks. So we conducted the RECs between September 2020 and April 2021. And for the first time ever, we used entirely self-administered modes of data collection. Respondents had the option to respond via web or by mail. And this allowed us to expand to our largest responding sample ever, 18,496 households. The larger sample size has enabled us to publish data and estimates for all 50 states and DC for the first time in program history. And I'd like to acknowledge our contractors, IMG Crown and RTI, for their contribution to a successful RECs household survey data collection. Okay, so the next phase. After we collect data from our household respondents, we then collect household energy billing information directly from energy suppliers for the responding households. And this next phase is called the Energy Supplier Survey, or ESS. The ESS for the 2020 RECs was fielded from July of 2021 through March of 2022 and collected billing records for almost 30,000 energy accounts from electricity, natural gas, propane, and fuel oil suppliers. And the suppliers that we contacted ranged in size from large utilities to small local fuel oil delivery businesses. And the ESS was successfully completed in collaboration with our contractors Leidos and Westat. So finally, once we have all of the housing characteristics from the responding households and their corresponding energy supplier data, we can complete our end-use estimation process. And Greg is going to give you much more information about this later in the webinar. So we produce estimates for over 100 energy end-use combinations and publish around 26 distinct end uses. Some examples of our published end uses are for space heating and air conditioning, as well as smaller end uses such as the energy used by primary TVs and ceiling fans. So at this point, you may be asking yourselves, why is EIA keeping all of this end use data to themselves? We have data for over 100 end uses. Why don't all of you see it? Why don't our data users have access to it? So for some end uses, we may have gotten too few sampled households using the end use. Or the end use might be such a small share of household energy use that it wouldn't even be useful to publish. And some examples of this are for small kitchen appliances, such as toaster ovens and coffee makers or blenders. So now let's dig into some of the consumption, expenditure, and end use highlights. So in 2020, the nation's 123.53 million households consumed 76.8 million BTU of energy on average. And this includes all energy used by a household, including electricity and natural gas or propane or fuel oil if a household uses any of those fuels. And I should note, this is not a statistically significant difference from the 77.1 million BTU of energy used on average by households in the 2015 RECs. So while the average household consumed 76.8 million BTU of site energy in 2020, there were variations in energy consumption by state. The average site energy a household uses is largely correlated with the average outdoor temperature. Households in colder climates, where space heating equipment is used more intensely, tend to consume more site energy than households in warmer parts of the country. So as you can see, in the bottom right-hand corner of this graphic, Hawaii was the warmest state, and using an average of 30.3 million BTU of energy per household. Only 6% of homes in Hawaii were heated, and just 57% of households used air conditioning equipment. Conversely, in the top left-hand corner of the graphic, Alaska was the coldest state, using an average of 125.1 million BTU per household in 2020. And in Alaska, 99% of homes used space heating equipment, while only 7% of homes used AC equipment. And I do want to note that differences here between state level estimates in this graphic may not necessarily be statistically significant. Okay, so while the previous two slides discussed average energy consumption per household, another useful measure is energy expenditures per square foot. By looking at this intensity by square foot, this helps us to make comparisons across households of different sizes, since square footage is such an important determinant of total household energy consumption. So the average energy expenditure per square foot for households in 2020 was $1.04, but there was variation by household characteristics. As you can see from this graphic, there are differences across many household characteristics, but I wanted to point out one difference in particular, and that's between households that own versus rent their homes. So renters pay 28 cents more per square foot for energy than owners. And some reasons for this may include that maybe a landlord is reluctant to invest in energy efficiencies for rentals, or maybe renters may not engage in energy saving behaviors, especially if their utilities are included in their rent. So now I'd like to turn to some of our end use estimates. So we refer to this graphic as the donut. And this particular donut is showing us the distribution of electricity end uses. As you can see, air conditioning is the most intensive electricity end use, accounting for 19% of total US residential electricity consumption in 2020. And this isn't surprising, given that 89% of US households used air conditioning, and residential air conditioning equipment uses electricity almost exclusively. So space heating and water heating are also large electricity end uses, but not as large as air conditioning because households may use natural gas or propane or fuel oil for heating. And in fact, if this donut was displaying end uses across all energy sources, we would see that space heating is the largest overall energy end use in homes, accounting for 42%, of household site energy consumption. And please keep in mind, whenever we're talking about space heating here as an end use, we're including both main and secondary space heating sources. And then on the right side of this graphic, you can see a bunch of smaller electricity end uses, including a new end use for 2020, electric vehicle charging. So in REX, we produce statistics on both total household site consumption by end use, as well as average consumption per household by end use. So many households may use an end use, but if it has a low energy intensity, it may contribute little to the total household site consumption. It may also be possible for a smaller percentage of households to use an end use, but if it's more intensive, it may contribute to a larger share of the total. So I have a few slides here to illustrate this point. So first, let's consider this graphic without any data points. We're only talking about electricity end uses here. The x-axis is the percentage of US homes using an end use, and the y-axis is average kilowatt hours consumed by the end use. And the curved lines are total electricity site consumption across all households expressed in terawatt hours. So clothes washers are used by a large proportion of households, but they use relatively little electricity within the household. So even though most households have a clothes washer, they're only contributing about 5 terawatt hours to total household site consumption. On the left, you see a dot for hot tub heating. Less than 5% of households have electric hot tub heating, but hot tub heaters use much more energy on average than clothes washers. So even though clothes washers are used in almost 85% of households and electric hot tub heaters in less than 5%, they're both contributing about the same amount of electricity consumption to the total because electric hot tub heaters are much more energy intensive than clothes washers. Okay, so now we've added in a few more electricity end uses. All of them are more energy intensive on average than our first two examples. So as you saw in the donut graphic earlier, air conditioning or space cooling is the most intensive electricity end use, accounting for 19% of total US household site electricity consumption. And it's the only end use in this graphic right now with over 200 terawatt hours of total consumption. Then as we move left, you can see electric space heating and water heating. And around 50% of households use electric space heating or electric water heating, which are both intensive end uses. So they account for 12% of the total each. Now, finally, if you go all the way to the left, you'll see our new end use, electric vehicle or EV charging. So because so few households charged an electric vehicle at home, it contributed very little to total electricity consumption, similar to the contributions of clothes washers and hot tub heaters. However, it is a very intensive end use for households that charge electric vehicles, using slightly less than 2,500 kilowatt hours per household on average, which is on par with the average electricity consumed for households with electric space heating or electric water heating. And finally, in case you're interested, we plotted all of the published electricity end uses onto this same graphic. All right, so now I'd like to turn it over to my colleague, Liz Holland, who is going to walk you through a very exciting new REX product.
Thank you, Carolyn. And I'm delighted to join all of you today to talk about our new interactive dashboard. Next slide, please. Thank you. As some of you may have seen, we recently released a dashboard with selected consumption expenditures information and household characteristics. Our aim was not only to provide visualizations of the state level estimates that we now have available with the 2020 RECs, but also to collect your feedback in order to plan our data products for the next RECs. So please explore the dashboard and let us know what you think. You can find it on the REC's website or use the direct link. Bill will also be copying it into the chat. And on the next slide, I'd like to describe some of the dashboard features. First, all of the navigation starts from the left-hand side, and there are a total of 20 measures and unique maps to choose from. Secondly, you can click on the Contact Us link to directly email us any of your feedback. Third, we have the ability to expand panels. In the upper right corner of each panel or section, you can click on the arrows icon. For instance, if you want to see a larger view of the map or the bar chart, and by clicking a second time, it'll go back to the original dashboard layout. Fourth, there is the ability to select states individually on the map. After you've selected a measure, from the left navigation panel, you can use the map to explore individual state values by clicking directly on them. Please note, though, if you'd like to see the household characteristic estimates that are on the right-hand section under the state label, then simply use the state drop-down menu on the left navigation panel, and those will update accordingly. Next, we also have the legend. It's denoted by the number 5, and by default, it is minimized. So all you need to do is simply click on the button that'll open and show you the legend for the respective map you're viewing. And then finally, next to the legend, we have a bookmarks feature. You can pan and zoom in the map as you would in a different standard map, but the bookmarks offer a shortcut to navigate directly to Alaska, Hawaii, District of Columbia, and the Northeast states. And you can always reset the map to its default view by using the home button. Again, we'd really love to hear your feedback. Please let us know how you're using the dashboard, what you think of it, and any enhancements or products you'd like to see in the future. You can, again, either use that Contact Us link directly from the dashboard or send us an email. Our address will be provided at the end of the webinar. And now I'd like to introduce Greg Lawson, who will discuss the 2020 RECs end use estimation methodology.
All right, thank you, Liz. Again, I'm Greg Lawson. I manage the end use estimation portion of RECs. And I'm going to walk you through our methodology and some of the updates that we made for the 2020 RECs. At the heart of what I will show is an example applied to a simple home. Okay, onto the methodology. I want to first emphasize that end-use energy consumption is not something that we can easily measure, and it is untenable to try to do so in a nationally representative way. So we really must estimate it. So how do we estimate it? Well, we use all the information available to us. Broadly, we end up blending the information in our end-use expectations, and we combine them with the information in our measurements of total energy. So expectations, you'll hear me mention that a lot. This is the output from our models. Quantified by our end-use models is our end-use expectations, and we construct these models based on a lot, but especially on wider community knowledge. So all those papers and studies that people publish and put in the literature, including technical support documents for efficiency standards, are very valuable to us, and it tells us the state of the art, state of the science. So we build our models based on that, but we must tailor our models to use the housing characteristics that we collect in our household survey, and also any weather data that we can attach to homes in our samples. We apply these end-use models to individual homes, and we rely on our survey weights to help us come up with these nationally representative estimates. On the measurements are the billing data that we collect directly from utilities and bulk fuel distributors. These are administrative data that are kept for reasons of financial settlement, and we consider them to be very high-quality data. When we blend these together, we use a process that you'll hear me refer to as calibration. And I'm going to describe calibration further when we present the example ahead, but I just want to say now that one large improvement we made for the 2020 RECs is that we enabled what we call billing level calibration for electricity and for natural gas. That is to say, we were blending the information in the expectations for a particular bill with the measurements, the bill that we actually received. So a quick note about these measurements. We collect bills for as many cases as we can, and we don't get them all, but we get them for a large majority of our cases. And for those that we get, most of them look like the representative bills I've shown here, where you have, say, 13 bills that straddle the calendar year 2020. And our fuel totals for the calendar year 2020 are as simple as prorating along the edges and adding them up. And this is what we do for 95% of all the cases for which we get bills in both electricity and natural gas. And so we do minimal treatment on this high quality data for our fuel totals. So now I'm going to walk through a hierarchy of some of our end use models to give you a sense of how we form these end use expectations. So our models necessarily have to depend on the information that we collect from a home. So for something simple like a toaster, we have one question about it in our survey. So we will know whether a home has at least one toaster and that they use at least once a week. But that's it. So the end use model for something this simple is just an assignment of some representative value of electricity consumption for a year. And we get that from the literature, either from a field study where someone has measured it, or from some bespoke targeted campaign to estimate that. And so here, UEC stands for unit energy consumption. So moving up the hierarchy, for larger end uses, like a refrigerator, we ask more questions in our survey. And this allows for making a more nuanced and complicated model. So for a refrigerator, we'll ask, what's the size, categories of size, how old is it, so categorical age, what's its configuration, for instance, if it has 2 doors, is the freezer compartment above the refrigerator, and can you get ice service through the door? These characteristics allow us to leverage federal appliance efficiency standards for refrigerators. And in fact, another update for our 2020 RECs is many of our end-use models now based on published efficiency standards. So as an example, if you have a refrigerator and you know it has a top-mounted freezer with no ice service through the door, then it specifies which standard to apply in the refrigerator appliance efficiency standard. Then, once you know how old the refrigerator is, you can figure out which version of that standard to apply, the one that was active during when the fridge was manufactured. They were updated in 1993, 2001, and 2014 in this case. And then the size tells us how to actually evaluate the standard. And this then gives us an estimate for the maximum annual energy consumption that this refrigerator would be expected to use at DOE test procedure conditions in the year it was manufactured. So the test conditions say that the refrigerator should be in a room with an ambient temperature of 72 Fahrenheit and be subject to normal door openings. Now, we don't stop there. We also have evidence in the literature that insulation degrades over time in refrigerators and freezers. And so we have an aging effect that we scale from evidence in the literature. Also, we know that we no longer ask about Energy Star status of appliances in RECs, but we know that there's abundant number of them out there, and the Energy Star models they consume less energy. And so we fold in this information to our end use estimates for refrigerators by obtaining from EPA the market shares of Energy Star appliances and their relative performance values. And last, we know that not every refrigerator is in a room that's 72 Fahrenheit. And so we've actually built in now an ability to change our estimates for varying ambient room temperatures because refrigerators in warmer spaces consume more energy. So at the top of our hierarchy are the space conditioning models, and these are the largest and most complicated to model. The energy consumption clearly depends on many aspects, like the building size and what it's made of and where it's located and the weather that is experienced. It depends on its occupants' behaviors, choices, and ultimately the space conditioning equipment that is in place and what fuel it uses to achieve its space conditioning. The way we actually model this is we go after first a heating or a cooling load. And that's based on our estimates of what heat losses or heat gains the home has experienced through a season. And then after that, we model the energy used by particular equipment to meet that load. And that's based on the equipment's efficiency, which we also get from efficiency standards when they're applicable. Now, at this point, I want to note, in order to support this billing level calibration that I mentioned at the beginning, and which I will explain later, we had to enable all of our end use models to be able to give daily outputs of our expectations. We needed this to be able to sum them into arbitrary billing periods so that we can match them to the bills that we've received from the utilities. And for many end uses, like toasters, we have no basis upon which to assume some days or months are heavier usage than others. And so our expectations for a toaster is on a daily basis, it's that UEC value divided by 366 days. But for end uses like space conditioning, the extension to daily outputs comes naturally because the models relies on weather, and it's easy for us to collect daily weather values. Okay, now we're going to begin that simple example. What we're going to do is frame out the basics of calibration here, and we're going to follow this in annual calibration. So you'll notice annual terms used here, but then I'm going to extend it to the billing level afterwards. So consider a hypothetical house that may have been in RECs, and it has only 3 end uses of electricity. So it's unrealistic, right? There's no lighting or anything, but this is just an example to hopefully get this point across to you. We've administered the survey and we have all the necessary housing characteristics. We've gone out and obtained the weather, the temperature and the dew point temperature that we need, and we've collected the electricity bills for this home, and we've summed them up to an annual total of 2,000 kilowatt hours. So before consulting any of our end use expectations, it's worth noting you have 3 end uses and you know the total is 2,000 kilowatt hours. There are very many combinations of end use estimates that would sum to 2,000. And you can think of this calibration process I'm going to explain as the process for finding the best combination, or what you might call the optimal solution. So in this example, we're going to show you 2 of the solutions that we have used in the past. So to find our expectations, we're going to consult our end use models that we've built. And so these are completely plausible estimates that may have come out for this house. So we're going to say the air conditioner is expected to use 1,000 kilowatt hours in 2020, the refrigerator 500 kilowatt hours, and the coffee maker 60 kilowatt hours. If you sum these, we expect this home to have used 1,560 kilowatt hours in 2020. And you'll note that this is 440 kilowatt hours less, so there's a deficit here, than the annualized billing total. So calibration is going to somehow correct these end use estimates so that they sum to that 2,000 kilowatt hours. One straightforward approach to doing this is to simply prorate that 440 kilowatt hour deficit across our 3 end uses in proportion to the size of our end use expectation. So the way I'm going to achieve that here mathematically is just going to take the share of the AC, 1,000 kilowatt hours, divide it by the predicted total, and then multiply it by the new total, 2,000. And so by construction, we end up with these final bold end use estimates, and they indeed sum to 2,000 kilowatt hours. So are we done? Well, it may not be obvious from the math here, but this is implicitly assuming that all 3 of these models, the output is equally valid. And we ask, is this the right thing to do? And we will quickly answer, we don't think so. We collect, as I've gone through the hierarchy, we collect different amounts of information for each end use. And in fact, some are just innately more difficult to model than others. And so we think that we really ought to have different levels of uncertainty attached to each end use estimate or end use expectation that comes from our models. And so we're going to now move forward and look for a calibration approach that can exploit and take advantage of these different uncertainties. So we have to actually use a bit of expert judgment to come up with estimates for the uncertainty that comes out of a model, but we believe it is possible to do this. And we have gone through and audited each of our end use models, and we have done the error propagation from the inputs and each crucial modeling assumption that we have to make along the way. and have ascribed a relative uncertainty to each of them. So these aren't the exact values that we use. They're rounded to something nice for this example, but it's plausible that AC has about plus or minus 50% relative uncertainty. So what we might say is our end use expectation for air conditioning is about 1,000 plus or minus 500 kilowatt hours in the year 2020. Refrigerators have less uncertainty, say plus or minus 20%. So then our refrigerator estimate is more like 500 plus or minus 100 kilowatt hours. A coffee maker we ask very little about, so we'll ascribe it, say, 100% relative uncertainty. So we're looking at 60 plus or minus 60. And now that we've entered in to adding these absolute uncertainties, we want to address correlations between them. It's important, if they exist, to take them into account. These are carefully chosen. We expect no significant correlations between these end uses. But if we were dealing with, say, clothes washers and clothes dryers, you'd want to take that into account because let's say the reported usage was less than the true usage, that error would probably have the same sign as the clothes washer as the clothes dryer because it's the same respondent. So once we have these absolute uncertainties specified and the correlations, we can do our root sum square propagation, and we find that our expectation for this house is 1,560 plus or minus 513 kilowatt hours. And we find that measurement is within plus or minus, so that's good. Okay. A calibration approach that accesses and exploits uncertainties and correlations is a minimum variance estimation approach. And here we're going to weight our model estimates by an inverse of their variance covariance matrix. And in practice, we solve this through an optimization routine computer where we can apply constraints so that we don't get negative consumption. And we assume that the billing total has no uncertainty. But here I've chosen this judiciously so that you can get a glimpse at some of the math going on. And that 440 kilowatt hour deficit now, instead of prorating it according to the end use size, we're going to prorate it according to each end use's share of the total variance. So that 500 squared, if you could go back one slide, please. 500 squared is that 250,000 over the total variance below. And you can see this different end use estimates that come out of this. Thank you. Now you can go to slide 32. And if we go back to our original depiction of possible disaggregations, here are the two that we just found in our simple example. And these are probably among the best solutions that we could choose from all the possible ones out there. Is one likely better than the other? I mean, we would submit that on average, the minimum variance is probably better. And it is that we can claim that because we've supplied even more information into our estimation problem. And we think it's good information. So we're going to see it again now, the next slide, in a tabular form. You can see that the absolute uncertainty for our air conditioner was plus or minus 500. And in fact, this minimum variance estimation technique added most of that 440 that we needed to add to the air conditioner, because 440 is already less than 500. It's by far the most uncertain, and that probably scans with people's intuition. Now, the math we did, I hope that this actually just frames out end use estimation for everyone, how we can get rich information from our end use models driven by our housing characteristics, our wider community knowledge and weather, and we can have it pegged to our measurements. So this is what we hope to get across here, but in doing so, this example relied on annual totals. And so we know that most energy bills are issued approximately monthly. Further, I think we all have an innate sense that many end uses, and it's particularly the largest ones out there, exhibit marked seasonality. Space conditioning end uses are the most obvious, but it occurs in other end uses as well, like water heating and refrigerators and lighting and pool use and fans and even EV charging. And so we thought it prudent to try to do calibration using the monthly bills instead of collapsing everything down to an annual number. And so I'm going to try to talk you through how we achieve the extension from annual to billing level on one slide, the next slide, and it's going to be speaking from more or less a case study. So there's a lot going on, and I want to walk you through it methodically. This is all the results of a case where we did natural gas calibration. It is a single-family detached home in North Carolina that uses natural gas for space heating, which is here represented in green. It uses it for water heating, here represented in brown. And then I've lumped the other things together in blue, all other end uses, which I think is cooking and a natural gas dryer in this case. On the right side of the slide, you're going to see two bar charts. They share their same axes. The x-axis is the months in 2020. The y-axis is the monthly total of natural gas in units of thousands of BTUs. The top chart here shows the initial modeled expectation for each end use's consumption in each month. And so I've stacked them so that the sum, the top of the green in the wintertime there, is the total natural gas we would expect them to use in that month. And you can compare that total to the black bars, which are in fact the reported billing totals each month. The bottom bar chart shows the end product of calibration, and by construction now, those bar charts all stack exactly to those bills, the black lines. Now, it's worth pausing here and just noting that in the top chart, we can see that it looks like our modeled expectations for natural gas are consistently too low in the wintertime. And then yet we see in the summer, it's consistently a bit too high. And so with the inclusion now of this time axis into the problem by retaining the months, we get a sense that our models for this home, it's likely underdoing the natural gas consumption of space heating. It's likely overdoing it for water heating. Like you can just look at this and get that sense. And now we have to come up with mathematical machinery that can latch onto that and correct it. So we have to extend our minimum variance estimation calibration process to work at the billing level. In order to do that, you have to have initial values at the billing level. So I've already said that's why we have our models outputting things at a daily level so we can accrue them to match the billing units. But we also have to have their uncertainties and correlations at the billing level. This makes our variance covariance matrix 12 or 13 times as large in each dimension. And further, it forced us to figure out the correlations across bills. So we have to answer, how does water heating in January correlate with water heating consumption in June? Or how does space heating consumption in January correlate with water heating consumption in June? So we wrestled with these questions and came up with what we thought were good answers to those. And we were able to code them up and extend our procedure to handle this. And we gave it to our optimization program. And we have the results summarized here in the left table. So in the very right-hand column, those are the totals. So from an annual point of view, we expected there to be 79.8 million BTU of natural gas consumed by this house in 2020. And when we got the bills and added them up, it was 84.7. And calibration does, in fact, add the 4.9 necessary. But when you look at the individual end uses in this case, we see that space heating in green, space heating went up by 10 million BTU. Whereas water heating dropped that 4.9. And so the change in space heating was actually twice what happened to natural gas overall. And this kind of calibration change was not possible in the annual calibration approach that I highlighted in our previous example. But now in our billing level approach, we can allow for these. And we have gone through careful inspection of many such case studies in both electricity and natural gas, and we are convinced that this new approach leads to more accurate end-use estimates. Then I'm going to just end by showing that same donut chart that Carolyn showed earlier, but now I'm going to show it side by side with donut charts for the other three fuels that we include in our total site energy consumption. So the top left is for electricity, site consumption, the top right, natural gas, lower left is propane, lower right is fuel oil. And I have plotted all the donuts the same size, though they really do represent different fractions or shares of total energy. The largest contributor to site energy was electricity, 47% of it, followed closely by natural gas at 45%. And the colors in these donuts are the same. So you can see that space heating, though it's the second largest individual end use of electricity, it's by far the largest of the other fuels, which is why it is the primacy that was shown in that scatter plot of that Carolyn showed, where temperature seems to correlate well with total energy use by homes. Now I'm going to pass it back to Carolyn.
All right. Thanks, Greg. So even before we finished up the 2020 Rex, we started thinking about the next Rex, and we're pleased to be able to share some updates with you. So first, we are planning on a 2024 Rex with data collection beginning in fall of 2024. We're building on our successes from 2020. We're going to be keeping a larger sample size and continuing to conduct the survey by mail and web. And that's going to enable us to continue to produce state level estimates for all 50 states and DC. We've been meeting to discuss what updates we need to make to our questionnaire to capture changes in household energy use. And we're still discussing two optional tasks. The first one is we're looking into producing some small area estimates. And the second one is we're looking into conducting a second larger multifamily building study pilot. So those are still, like I said, optional, but we're still thinking about those. And finally, we're continuing to think about some new data products, including data visualizations like the ArcGIS dashboard that Liz shared with you. And so as we continue to plan for 2024, we would love to hear from you, our stakeholders, about any new Rex products you would like to see, or other ways that we could just get more out of the data and find new uses for Rex. And if you would like to share an idea with us, please email our inbox at EIA info consumption and efficiency at EIA.gov. And this is also on our, this email address is also on our website because I realize it's pretty long. Okay, so that wraps up our prepared content for today. So now we're ready to take some questions. And as I said earlier, my colleague, Bill McNary, will be feeding Liz and Greg and I questions from the chat.
Okay. First question is whether or not we're considering expanding to include anything like dorms or group quarters, military barracks, anything like that.
So we are not. I think the unit of analysis for Rex has potentially always been primary occupied housing units, not including group quarters. And part of that is because for those of you who use a lot of EIA data, we have our sister survey, the Commercial Buildings Energy Consumption Survey, and dormitories or nursing homes or those other types of group quarters are included in the CBACS sample. Additionally, we are aware that there's a lot of interest in getting multifamily building energy consumption data at the building level. So keep in mind, Rex samples units in multifamily buildings, but we're not getting the energy use for the entire building. So I live here in Washington, D.C., and there's tons of buildings around with like a Whole Foods on the bottom and then residential, and maybe the residential has a pool and hallways and a parking garage. So right now, we're not getting the energy consumption for that Whole Foods or the pool or whatever. But so we're hoping as we keep working on these multifamily building study pilots to be able to capture the energy use of the entire multifamily building.
Okay. Next one is if we could go back to slide 10. There was a question on why we suspect there's a disparity in household income.
Oh, on
Energy consumption per square footage. Yeah.
Sure. Okay, so some things to keep in mind, and I want to note that this graphic is actually comes from a Today in Energy article that myself and my colleague Ross Bell wrote. So if you want to see like the whole article, you can find it on EIA's Today in Energy. So by household income, so we're looking at expenditures per square foot. So something to keep in mind is that let's say you live in a 500 square foot apartment. There's certain things like your refrigerator or a TV or other things that we like all use or cooking. And you have that in a 500 square foot apartment, you probably have a very similar refrigerator, stove, etc., in a 3,000 square foot house. So when you take the expenditures and divide them by square footage, the intensity is going to look a little higher per square foot in the smaller apartment. So what we think, we don't know, we haven't run a regression on this, is that okay, potentially for people living, or I'm sorry, people, households earning less than $10,000 or in those lower income brackets, maybe they're living in smaller housing. So we might expect there to be a little bit higher intensity. However, other things can be, you see this disparity between owners and renters. Maybe people at lower income levels are more likely to rent, or maybe they're living in less efficient housing. Like I said, from this graphic alone, this is just frequencies. We're not controlling for these different things, but those might just be some of the reasons why there might be higher intensities or higher expenditures per square foot at the lower income levels.
All right. We had a couple questions asking if we have any plans to try to include Puerto Rico or other U.S. territories.
So not at this time. We know there's a lot of interest in data on Puerto Rico, but as of right now, EIA does not have plans to move forward with the RECs in Puerto Rico.
Okay. Also, are there any plans to include any kind of sub-meeting or verification of a subset of homes as part of RECs?
No, not at this time. Again, something that we've talked about and thought about, but it just doesn't seem like that's going to come together for 2024. Bill, I think you're muted if you're talking.
The next question is whether or not the uncertainties for each end use are published anywhere.
Oh, I'm going to kick that to Greg.
Yes, that's for Greg.
Okay, they are not currently published. We have to ascribe uncertainties for all of the end uses that Carolyn talked about. There's over 100, but we only publish a subset. So we hadn't thought to try to publish just those that were, to make public the uncertainties for the ones that we publish. But I don't think that there'd be a reason to withhold that. So we might be able to do that in the future. I don't know if we'll go back and do it for 2020 or not. Something we'll have to talk about internally. It's a good question. We wouldn't be able to do all of them, but we could ascribe it to the ones we at least publish estimates from.
Okay. What do we do about energy use in detached garages or outbuildings, things like that?
Carolyn, do you want to do it, or who do you want
take
to?
this one?
Okay, so previous recs did ask about detached garages, but the current recs only asked if you have an attached garage. If that outbuilding or the detached garage's consumption is included on the main meter, then it would be included in the bills that we get. We do still ask if garages, no, it would be only for attached garages if they're conditioned. But there's a chance that the consumption from such outbuildings could be especially if they disclose the activities that would go on in that building. If, however, during editing, we find that there's an outbuilding and it looks like maybe it was a source of something that isn't residential consumption, something like a side business or like a farm, something like that, then it might be cause to exclude either the bills or potentially even the home from our sample, because we were looking only at primary residential consumption. So it gets tricky and it's generally dealt with in our editing process.
Yeah, I was just going to add that we we don't we encourage our respondents to give us the characteristics of the their home or their, to try to get them to focus on the home. But, whenever you're collecting data from the public, there's always a range. So as Greg said, we do some editing around that to try to um, eliminate any detached garages or buildings or farm buildings or anything that we didn't intend to be included um, in the household survey.
Okay, next one is a question comparing REX data for California to the residential appliance saturation survey. Wondering why, if we have any idea why REX shows 19% electric water heating, whereas RAS only shows 11% electric water heating.
So this is a tricky comparison for us to make. We didn't administer the RAS. One thing I will oh, Carolyn, looks like you have an answer at the ready. Sorry. I mean to
Oh,
preempt you.
yeah, I was just going to mention, and Greg, you can correct me if I'm wrong. The RAS is conducted in conjunction with the large utilities, correct?
Mm-hmm.
So, so it's probably potentially eliminate not covering rural areas that are not covered by those large utilities. So where the REX is covering is representative of the entire state.
So
Go
other
ahead,
energy
Greg.
suppliers, yes. So another thing that we have found kind of empirically that knowing your water heating fuel is not always the easiest thing for respondents to know. And so we have some advantage over other surveys in that we have both what the respondent tells us is their fuel, but also their electricity or natural gas or whatever bills, propane. And in some occasions, we can actually reconcile the two. And that's something that we have done, and it mainly shows up in space heating. So it's pretty easy to see if someone says they have electric space heating, but their bills show that they actually have natural gas space heating. It's not too hard to confidently change that, but occasionally we can do that in water heating as well. I'm not going to say that ours is a better number, but there's another thing that could contribute.
All right. And again, there's a lot of questions we're not going to get to, so I'll be responding, or someone will be responding to all of those from the chat. But I guess about three more, I think, that are general questions that I think will help everybody. I guess the first one is there any reason that with the improvements in the 2020 modeling that the 2015 or older data should be seen as less reliable, or is 2020 that much better?
Well, I just gave a presentation about how we're happier with our calibration process. However, it's also a much bigger sample than it was in 2015, and it's hard to intercompare RECs. Everyone is an individual study with different people working on it, different contractors, different sample. The 2015 sample was clustered because we intended to do it through CAPI mode at first. So there's a lot of differences between them. I think the 2015 data stands on its own. It has relative standard errors published with their estimates, but at the same time, we are happy with the progress we made for 2020.
All right. Two more questions. Greg, you get 1 minute to answer each of them. The first one is, how do we treat wood and wood pellets as a fuel?
Okay, so wood is self-reported. There is no ESS where we can go to people's wood suppliers. And so we trust our respondents. They, on the survey, can tell us whether they use it for space heating and or water heating. And we do model the consumption that we expect them to use for those. And there's no careful calibration if they tell us their wood consumption, and it's categorical, in fact, for whether it's pellets or cordwood. And for those who don't tell us, we have to impute it, which is to say we have to estimate it. And we have methods for that. I think those are the salient points. Is there anything to add, Karen?
No, that's good. And then the final one is, briefly, how do we handle on-site PV?
On-site PV, like
Yep.
photovoltaic, is that what the question was?
Yep.
So, okay, we do ask as part of the household questionnaire, does your home have any on-site generation? And solar photovoltaic is one option. It's the most common option by far. Not many homes have their own wind turbines. And if they say that, we then ask follow-on questions about like when was it installed and how big was the system. Not sure about the data quality of some of those replies, but if a respondent did tell us that they have solar, then it becomes an issue for our team when we're collecting their bills. If we determine, so REX is a residential energy consumption survey. It's not a survey of how much electricity people buy from the grid, it's how much do they consume. And so if we definitely want to include the part that they self-generate, self-consume from their panels. And if we determine that the electricity bills that we get from their suppliers is only the portion that they purchased from the grid, then we will have to unfortunately let those bills go and estimate the consumption through imputation. Luckily, that's a small number in the relative sense of our sample, but it is the procedure that we're doing for now. We hope in the future to be able to collect data directly from residential, like microinverters, companies, something like that. That's a pipe dream of ours. There's no plans to do that, but it's something we've talked about in our team and would love to have that missing piece of the puzzle. But for now, how I described is how we handle it.
All right. Oh, perfect. Thank you, Ross, for going to this final slide. So, thank you, everyone. As Bill said, we're going to follow up. If we didn't get to your question, we have your contact information and we will get back to you. And just a reminder, if you ever have questions for us or need help finding a stat or whatever, you can always email us at our inbox. Here it is again, EIA info consumption and efficiency at EIA.gov. And like I said, it's linked at the website there. So, all right. Thank you. Have a great afternoon.